Hey, welcome back to Chemistry with Mrs. Mays. Today we're going to learn about colligative properties, so we can talk about the influence that a solute has on the properties of the solvent it's dissolved in. First of all, let's define what colligative properties are. Basically, these are properties that deal with the number of particles that are dissolved in a given mass of solvent. The physical properties of a solution will be different from the properties of just the solvent all by itself. A pure solvent may have a vapor pressure that is usually higher. So we call this vapor pressure lowering because a solute lowers the vapor pressure. And that results in boiling point elevation, because adding a solute to a substance causes the boiling point to increase. And finally, we have freezing point depression, because adding a solute to a pure solvent results in a lower freezing point, freezing temperature. To understand what's going on, we need to learn how to work with the Van't Hoff factor. Little I describes the number of particles into which the added solute dissociates. So we're going to break apart ions that are aqueous into their particles. For all molecular compounds, the Van't Hoff factor is equal to 1, because for something like glucose that is made from 6 carbons, 12 hydrogens, and 6 oxygens, there are no ions in the solution. The particle doesn't break apart into ions or charged particles, it just dissolves in the water all in one piece. So that Van't Hoff factor is 1. For ionic compounds, the ones that completely dissolve in the solvent, usually water, but not always, then the Van't Hoff factor is dependent on the number of ions that we get when that particle is dissolved. So here's the example of sodium chloride. You guys have been with me long enough to know how this breaks apart. The sodium has a +1 charge, and the chloride has a -1 charge. So when sodium chloride dissolves in water, it makes 2 particles. Therefore, its Van't Hoff factor is 2. Suppose that sodium phosphate broke apart. When sodium phosphate breaks, remember I have 3 sodiums now, and only 1 phosphate. Phosphate is a polyatomic ion that stays together. So how many total particles is this? I have 3 sodiums and 1 phosphate. So the Van't Hoff factor will be 4, because there's a total of 4 ions in the solution. For colligative properties, the identity of the particles is not important. It's just how many of them there are. So the size, the molar mass, they don't matter. It's the number of dissociated particles that's what is important. Let's look at vapor pressure lowering specifically. Vapor pressure is the pressure exerted by a gas that is in dynamic equilibrium with its liquid in a closed system. So if you have a closed container and you have liquid particles at the bottom, some of those liquid particles evaporate and create a vapor phase or gas phase, right? And as those vapors bump into one another, some of them will return or recondense back into the liquid phase, and that's why it's called an equilibrium. When the solutes are added to the pure solvent, the vapor pressure is lowered because, the vapor pressure is lowered because not as many of those particles on the surface have access to the open space. That means fewer surface molecules escape from the liquid phase into the gas phase. The decrease in the vapor pressure is proportional to the number of solute particles that are dissolved in our solution. The more particles there are blocking them from the surface, then the more the more the vapor pressure is affected. The vapor pressure decreases when a non-volatile solute is added to our solvent. So here's how that works. We have a pure solvent on the left, and if I put solute particles, the red particles, into my solution, then some of them are blocking the evaporation. So some of the liquid can't get into the vapor phase. Another thing that might happen is that there's an attraction of the solute particles for the solute particles, and they sort of stick together, and they don't want to let go. They don't want to go up into the gas phase. But watch out, because if we have a volatile solute, suppose that we have a solute that likes to evaporate. A volatile solute added to a solvent will increase the vapor pressure because the volatile solute has its own vapor pressure that adds to the vapor pressure of your solvent. So vapor pressure lowering is valid for a non-volatile solute, but if you have a solute that evaporates readily, which is what volatile means, then it will add to the vapor pressure and increase the vapor pressure of your solution. So this is going to impact the boiling point. The boiling point elevation basically describes why adding a non-volatile solute is going to require more energy to be added. So when a non-volatile solute is added to the solution, the boiling point of the solution will increase over that of the pure solvent. Boiling point simply describes the temperature where the vapor pressure of the liquid equals or exceeds atmospheric pressure. Once the vapor pressure is more than the atmospheric pressure, your liquid can boil. So when a solute is added and the vapor pressure is decreased, that means we have to heat it up even more so that we can get that substance to boil. Additional kinetic energy is required to break apart any attractions between solute and solvent. Let's take a look at an animation so that we can see what is this boiling thing all about. So here's our vapor pressure. If we have pure water, some of the water molecules just above the liquid just get sort of bumped out into the gas phase. And as they bump into one another in the gas phase, they might recondense back into liquids. But this is our dynamic equilibrium that causes vapor pressure. When we put a non-volatile solute such as sodium chloride in, then you'll see the vapor pressure is less. So there's a lower vapor pressure because the sodium chloride particles that are in the solution are blocking the waters from getting up to the surface to evaporate. Plus, water has an attraction for those charged particles. Since water is a polar solvent, it sticks more to sodium and chlorine and doesn't leave the liquid phases easily. Boiling point elevation occurs because additional solute particles decrease the vapor pressure so that more pressure than normal would be needed to boil so we can overcome the atmosphere that's pushing down on us. More energy is needed to break the attractive forces between neighboring molecules and exert the additional vapor pressure required. Freezing point depression is describing the temperature difference between the freezing point of the solution and that of the pure solvent by itself. Solutes will disrupt the normal geometric pattern of the pure frozen solvent in a solution because they get in the way. The solute particles get in between the solvent particles, so additional kinetic energy has to be lost for crystallization, otherwise known as freezing, to occur within that liquid. So crystallization is how we get something to freeze, turning a liquid into a solid. So here's a picture of how that works. In System A, the pure solid can turn into a liquid because of the kinetic energy of the particles. So we have a shift from solid to liquid, or back from liquid to solid, because the particles fit into a geometric crystal pattern. But in System B, the red solute particles are getting in the way of new liquid phase molecules joining into the crystal so that the solvent can crystallize or freeze. So when the solute is blocking them, then it disrupts the normal crystal pattern and more kinetic energy has to be lost. That means a lower temperature is required before the solvent will freeze. So that's the impact that a solute can have on properties such as vapor pressure, boiling point, and freezing point. When we talk about other phase changes, then we'll talk about the forces between neighboring molecules, the IMFs, that make this happen. So we'll see you guys in class. Keep practicing.